Okay, let's go ahead and get started here with what we're going to cover today. Let me back up for just a second here. Okay, so what we're going to talk about today is an alternative to the tile-based worlds that we were dealing with for side-scrolling or top-down or 2.5D type games previously. And this is a related method of doing this, but has a few differences. So let's do a quick review of the tile-based worlds. And essentially one of the advantages of the tile-based system is that it allows for these kind of large game world spaces to be created. So think of games like Terraria. We have this really large world space, and in that large world space you have various types of terrain, various types of objects, and you in some cases can mine and interact with those, and you change that. And the tile-based systems, what they all kind of have in common is that they all use some sort of a grid. Like think of graph paper. And in each of the cells of that paper, there's a reference that says what type of tile that is in that space. And then that is used to actually draw the world from the tiles that are located in that grid, all being essentially like stitched together into one large space there. And one of the things that we saw in those previous examples that we did was we kind of use these little 2-character strings to represent each of the tiles. And since you have, with those 2-character strings, you have a lot of possibilities for, the cat is getting in front of me here. There we go. All right. But since there are a lot of possible ways you can do that, you can have a very rich set of tiles that you could use to create your world. But one of the things about those is every texture and every tile was the same dimensions. In other words, if you have this square tile shape, everything is created out of the square tiles of the same shape. If you want larger structures, you've got to use multiple tiles to do that. But they all have to be that kind of same dimension, or they won't stitch together properly in that grid. Now, in the previous examples that we did with the tile-based world, we had, for example, the 2 character string D1 might be brick texture type 1, L1 is ladder, G1 is grass, I1 is ice. And so you basically stitch the world together out of these components, and that's what we did in the previous example. That we had maps were created just stored like this in the text format, but when they're drawn on the screen, the program says, oh, B1, I have a texture for that, plugs it in, and we get the brick textures for that. And so that can be a really useful way to store the thing. And the nice thing about that is that means we can make new levels without having to make graphics and create new art assets, because it's going to be put together out of the textures we've already created, out of the tiles we've already created. And that's a really common thing. For example, the original Nintendo NES system, most of the games on that were all done with tiles, because that was built into the Nintendo NES to have hardware to load tiles from memory and put them on the screen. And so most of the games came out using that in some way. Some of them didn't, most of them did. Now, to finish off our kind of review of what we did before, is we have this map string that looks like this. I have it set here as individual strings, but really it could all be put together into one big string with new lines in between. So this bunch of characters turns into this picture being shown on the screen for this level. So in other words, wherever you have a B1, we get bricks. Wherever we have L1, we get ladder. And then notice that we have a little character here that's this eyeball. That little eyeball character down there, that is a sprite, but that is layered on top of this. So in other words, we draw the background with this, we draw the sprite, but notice it still interacts with it. It sits on the brick. And we added some functions to allow it to do that by saying, hey, is this object colliding with any tile? If it is, what tile type is it that it's colliding with? So those can be rendered along with the tiles and then interact with them in some way. Now, we also kind of extended that idea to create these large world spaces. And when we created those larger world spaces like that, it allowed kind of the window into a larger world. So in other words, we just have this larger set of strings to make a larger world space. We now have defined in our program this window that looks into that world and renders wherever we are in there. And so as the eyeball moves around, the window just follows it. And so we can have it climb ladders and jump over chasms and walk across the grass without colliding with it, but then land on the platforms. And so we have this ability to create this window into this larger world that works like this. So in other words, this is the rendered view of this little window, but if the eyeball were to go to the right and walk this way, the camera window, the red rectangle here, would follow, and we'd see more of the world get revealed. And we can extend this to any size world we want. But notice that it's still composed of same size tiles placed on a grid, and we can make the grid larger or smaller. In other words, we can have larger graph paper, or we could even have this stuff get procedurally generated and add the strings in kind of automatically through code, but it's still a grid of tiles that are all uniform size. Now, one of the things that we had to do in order to do that conversion between the world and the screen is we had to have a way to convert between the two coordinate systems. In other words, when we're tracking an object or even a tile, like let's say this end of this platform down here where that B1 is, that exists somewhere in our world space. In other words, we have kind of world coordinates that control where everything is, but then as we move this window around or the camera around to follow things, some things are going to end up, when they get drawn, they're going to have to be drawn on the window itself, or the kind of the camera frame space. So we have to have a way to translate between them. In other words, all of the drawing onto the screen is going to happen in screen coordinates, but everything is going to move around and be tracked in world coordinates out here. So we need a way to translate between them. And the easiest way to translate between them to explain is really, it's simple to do. It's just a subtraction. So for example, if we have some object, let's say this object here, this purple circle, and we want to know where is it on the screen in screen coordinates, all we really have to do is subtract off the Windows X from the X of the object, the Windows Y from the Y of the object, and that'll tell us where it is on the screen. So in other words, we want to figure out how far over it is from the edge of the window. So if object WX is here, window X is this XY is this upper left corner. So in other words, we're saying how far is it from, let me back up. We're saying how far is it from this corner to that, and the easy answer to that is take this WX here, object WX. How do I get the distance from that? We'll take it and subtract off the window X. So really we're computing the distance between here, the edge of this window, and the X of the object. And some objects will end up being off the screen because of that, like this object where it's drawn right now. Some of them will be on the screen, like anything that's inside of this red rectangle. And we do the same thing for Y. And that gives us the object's screen X and screen Y position based on its world X and world Y. And we're going to be computing that as we go. And as we start writing our code, we're going to actually write our code in such a way that we're going to keep track of everything in the world space, convert it to screen space when we go to render things on the screen. Now, sometimes we might need to go the other way, where we go from screen to world coordinates. An example of that might be you want to have the game interact when you click on a space to have something happen there, like click here to place a bomb, or click here to destroy one of these brick platforms. And so when you click on you're clicking on the screen, you have screen coordinates, but you need to know where in the world are you interacting with that thing. And to do that, it's really just taking these same assignments we had up here, but solving that. If you think about that as an equation, solve it for world X in terms of screen X and window X. And so notice that it's really the same thing, but we'll just say take the screen X, where is it on the screen, add 2 at the window X, and that'll give us the world X. So it's really the same two formulas, just manipulated into solving for the world X in terms of screen X and window X. And so the idea there is when we're doing this conversion from world space to screen space, if something ends up off the screen, don't render it. We only have to worry about rendering things that are on the screen. In other words, there's no reason to try to render this block down here in the corner, this brick in the corner, because no one's going to see it right now. So in other words, as the camera moves, if we can figure out what things are on the screen and which things are off the screen, or which things screen coordinates make it visible and which make it not visible, then we can draw things optimize the code and that allows us to have really large world spaces that still run really quickly because we're ignoring anything except for what's inside of the window. And this is stuff we've done before. Now, the tile-based system can be really good for creating large worlds, and it's also really good because we can update data, like a file that's storing the data to make all of this where the platforms are. So you can store levels in files in a simple text format without having to involve creating new artwork for them. So as long as we have a rich set of tiles, we can make really rich worlds, and we can modify them to a lot of different formats and a lot of different ways to create that. Now, some pros and cons of those tile-based systems. The good is that worlds and levels are easily changed by just changing the data. In fact, you could give players a level editor to use, and they could create the things and save off the files that have all the text patterns and then load up, and the graphics would be different. So they wouldn't have to be artists. You wouldn't have to rely on them to set up everything. It could all be done through a data representation. Also notice the world size can be really large with that, because especially if we add those optimizations to only worry about rendering things that are inside of the screen space, even with a immensely large world, there's going to be a lot of data that we have to sort through or store for that. But the world space can be large, and it'll still be fairly quick if we only are worrying about things that are visible. The graphics don't have to be edited by hand. You don't need an artist to do that. You don't have to know how to use Photoshop or any other tools. Basically, as long as you have the tiles, it'll tile it automatically and create a new look to the game, or a new level, or whatever you want to create. Also, these are related. You don't have to edit any graphics to change the world. You could just edit the text file, edit the configuration file, and then you have a totally different kind of world space. All right, the bad things, though, is notice that we're kind of restricted to how we represent this we're restricted to having this grid of same-size cells. So there are some systems where you could use like certain tile types that take up 4 cells, like in a larger square. But more often than not, it's all same-size tiles. And if you want to have some entity that's larger, you just use a group of tiles together. And notice that all of the tiles need to be processed, even if they're empty. In other words, when we're going to draw something on the screen, we have to know. Let's go back just for a second. We have to know and go through every tile that's in the grid that's on the screen. Now, that's not going to be, depending on the tile size, that's not necessarily a large amount of work that we have to do there. But even if there's nothing being drawn, we have to go through and look and say, oh, nothing there, go to the next one, nothing, go to the next one. And so we have to process those. And if the world gets large enough, then that can use a significant amount of storage just to store all of the strings. But it takes a really large world to get to the point where that's using a lot of storage. But it's still much, much better to store that grid of tiles than it would be the graphic image of that size, especially for a large world. All right, so really the main restriction on the tile-based world stuff we looked at before was the restricted kind of grid size and the object size needing to be a multiple of tiles in order for it to work with it. In other words, if we're going to stitch all those little squares together, they have to be kind of uniform size or they won't match up properly. Now, what we're going to look at today is we're going to look at a approach that's similar to that, but a little bit different in that hopefully it'll overcome some of those bad aspects of the tile-based grid method we looked at before. And what I'm going to call this method is kind of a rectangular block world. And notice this is different than tiles. We're not dealing with tiles here. We're dealing with rectangular block objects. So think of it as some blocks might be square, some of them might be rectangular and long, some might be tall, some might be larger. And notice it's also not going to put a restriction on the size of them all having to be the same. So in this method, we're going to define our world not as a grid of cells, but as a list of rectangular blocks that make up the world. And so each block is a rectangle of some sort, meaning that it has an X and a Y for the upper left-hand corner of the block, and then a width and a height. Notice that each of those blocks can also exist at any location. In other words, unlike the tiles, it doesn't have to be on a grid. It can be anywhere. So the X and the Y don't have to be multiples of 32 or 64, whatever our block size is. They can really be anywhere we want to put them. They can also have any height and width, meaning that we're not going to restrict that to squares. We're not going to restrict it to all of them being uniform. They can be, each individual one can have any width and height, and it can be at any location. And that means that the location doesn't have to be on a grid multiple. Also, each of those rectangles, rectangular blocks is going to have some texture associated with it. And it might have a collision type associated with it. In other words, you want to collide with ground type objects that you land on and can jump. And ladder type objects allow you to climb. And I don't know, treasure type objects you can pick up from the map and get points for it. So this collision type thing can come in handy. We'll probably take a look at using that here later on. Now, continuing on from there, let's look at a simple class. This is misspelled. I'll fix that before I post it. We're going to use a simple class to represent each of the blocks. So each of the blocks, we have class block object, and what it's going to have in it is really just this kind of, and this needs to be updated. This should be left and top here instead of X and Y, but I'll fix that in when we actually live code this. But in other words, it's going to have an X, it's going to have a Y that gets set, and it's going to have a width and a height and width, a surface that's associated with it, and then whether it collides or not. It's either going to be true if it's allowed to collide, false if it's not. And if it is allowed to collide, it can have a collision type that we can set to say what type of collision type is this. And we'll look at that later on. So continuing on here, we want to create a list of those. So in order to create a list of those blocks, because this just allows us to create an object to store instances of those, but we want to keep a list. So we're going to use another class to do that. And the other class here, we're going to use this world object. And the world object here, the way that works, is essentially the world itself. In other words, this is the really large rectangle of the world that the little blocks are going to be placed into. And so the world itself has a height and a width. It's got a window into that world, which I'm going to call screen left and screen top, screen width and screen height. So in other words, this is kind of defining the window into the world. So the world itself has a width and a height, and it has a window that we're defining into it. And notice that we can pass in what we want, where we want the window to be, how wide, how tall, and where is the top left. So we're going to move this window around. So as we play the game, we have this large world, and inside that world we're going to have this kind of littler window, and the window is going to kind of move around as we play the game. Now, in order to get the blocks into the world, I have this add block method. And all that does is it adds a block object that we had on the previous slide to the end of this block list. So in other words, we're going to say add a block at this left and top position, or this X and Y position, with this surface type, this surface, and tell whether it collides or not. So we're adding that object into this list. In other words, this block list is just going to have a list of all of those block objects that make up our world. Now, we also have a render blocks kind of function here, and all that does is go through each of the blocks and then blit to the display the surface of that block at its XY position. Now, notice, though, that here's a subtraction going on, where I'm subtracting off block.x minus screen left, block.y minus screen top. And that is the conversion from world coordinates for the block to screen coordinates to render it on the screen. And notice in this case, I'm not doing any checks to see is it on the screen or not. I'm just blitting it no matter what. And I'm letting Pygame handle, hey, if it doesn't show up on the screen, the blit will just not end up doing anything. It'll have no effect. If I wanted to optimize this a little bit, I would probably put a check in here that says, hey, is this rectangle of this block, does that rectangle collide with the rectangle of the screen? And if it does, then I'll blit it. Otherwise, I'll skip it. But no matter what, we have to go through all of the blocks in this list. And there are ways to optimize that too, to say only go and check blocks that are within kind of a certain region of interest that we're in right now. So there are ways to optimize that by creating kind of a structure that can store when I'm in this part of the map, these are the types of blocks I have to worry about, and then you switch off which part of the map you're in. So there are ways to optimize that, but for right now we do that. And then just to show the boundary of the world, I kind of drew this rectangle that starts at the notice here again, converting world 0, 0 to screen 0, 0, and then width and height. So this is actually making a rectangle around the entirety of the world itself. And we'll see that here when we go to write the code. The last thing I did is I have this little function that just says, hey, does this left, top, width, and height, does this rectangle that I'm passing in, and I'm passing it in discretely by the x, the y, the width, and the height, does that collide with any blocks? And if it does, what types of blocks is it colliding with? And so to do that, I basically make this collide type list. It starts out empty. And if I find a block, and I make a rectangle here that corresponds with that stuff that was passed in exactly. And then I say, hey, if I go through and I do a rectangle.collideRect, in other words, if this rectangle that I just created around this rectangular set of coordinates, if that collides with this block, the block that I'm on, then and that's only if the block is allowed to collide. So if the block is allowed to collide and it collides with the rectangle we're checking, then I'm going to go ahead and add to my collide type list. I'm going to go ahead and add that block in, that block collide type. But if that collide type is not in the list or is already in the list, I leave it there. So in other words, I only want this to tell me something along the lines of, okay, you're colliding with a brick texture right now. But I don't need to know I'm colliding with 4 of them. I just need to know, am I hitting brick or am I not? So what I do at the end is if I say if the length of the collide type list is 0, I return false. In other words, this will say false if I'm not colliding with anything, and otherwise it'll return a list that I'm colliding with. Now, there may be easier ways to do this. We might divide this up into 2 different methods. One that is colliding, and then one is what types am I colliding with. But right now, we're just going to do it as if it returns false, we know it's not colliding with anything. We could also return none here, I suppose. But if it is colliding with something, it's going to tell me the list, give me the list of all of the types of things it's colliding with. Okay, now you could also add some logic around the type in the main once we get there. Okay, so to create a world, it basically devolves into, or it is comprised of a few steps here. In other words, we're going to load some images. We're going to create a world instance, so an instance of this object, and then we're going to add blocks to the world using the add block method based on the images, that surfaces that we loaded out. And that's going to be relatively easy because we're just saying, here are the types of images I want. I'm going to create a block to put them in different places. So for example, if I wanted to put a steel beam in my world somewhere, I'll say, here's where the steel beam starts, and I'm going to put it in the world in that place. If I want to add in a set of stairs, if I had created something like a set of stairs, or if I had created some sort of pit of spikes, I could just drag those things into my world, put them in the spot where I want them to be, and then save that off as a list of all things that get created. So after all the blocks have been added to the world, we can render them all using the render blocks method, and then we can use the collide blocks method to see if objects are colliding with them to get interaction between the sprites in the world and the block world itself. Okay, so here's what some block examples might look like. And looking at this, you might notice that, looking on the screen there, that you have some small ones, like here's a brick tile type thing that we used before. It's small, it's square, but we also have this like steel girder thing that I made, and that steel girder thing going across there, you'll notice that that's not the same size as the brick, and it's not even the same size as the steel beam thing that I made down here that has the little rivets in the side. So notice that we have different size blocks that we're creating, and then notice over here we also have this kind of pillar that we could use. So we could put pillars and then put a steel beam across the pillars, and we could put bricks like to make stairs or a platform going up to there. But we can, if we have just these 4 things, we can put them together in a lot of different ways. And we could also set some of them to be background or not colliding. For example, this pillar might be a background object that just sits in the back, so when the character goes across it, it just goes across the front of it. So it's more like decoration than it is something functional, where the girders and the bricks and the beam, that could be something that we collide with. Okay, so in our example, what we're going to do is we're just going to kind of load the images and randomly create some blocks in our world. So rather than hand placing all the objects, you'll notice what it is. I'm going to make a world that's fairly large, 10,000 by 10,000. And this is in terms of pixels. So this is 10,000 pixels by 10,000 pixels. That's a fairly large world space that we're creating. And then notice here, I load the surfaces up by loading up these images. And then I just randomly throw some of these around the world. In other words, here I'm creating 30 pillars. And notice I'm setting the collision of that to false, meaning make that a background object. So I'm making 30 pillars. I'm adding 200 of these brick blocks, and then 40 beams and 40 metal beams. So I'm putting, if we were to count all of this up, we've got 80, 280, 90, 300. We got 310 total blocks that we've added to our world. And that might seem like a lot, but it's really, if you think about a tile-based system where you have this grid of tiles, this is actually not a lot of objects that we created and added to our list. All right, so what we're going to do now is we're going to kind of switch gears here, and I'm going to switch away from the presentation mode that we have here, and we're just going to kind of live code this. So I'm going to switch over to the screen here. I'll come back to the summary of this in a second, so let me switch on the actual screen view here. Okay, so now we're actually looking at the screen rather than the presentation, so I'm going to minimize that. All right, and here I am in a Python shell, and I'm going to go ahead and make this window. There's a Python shell back here. I created a new window by doing Control-N or File New. And what I'm going to do here is I'm going to go ahead and make this window just a little bit bigger so it's a little easier to see. Let's do like that. And let me make sure that it's not interfering with anything or your visibility of any of it. And I'm going to go ahead and make the font just slightly larger too, so it's easier to see if you're watching this on a smaller device. Okay, so now hopefully you can see stuff in there when I type now. All right, so what I'm going to start with is, since we're going to be using Pygame for this example, well, let me first start off with a comment. Let's call this block world example code. All right, so there's a comment. And then what I'm going to do is, since we're going to be using Pygame, I'm going to import that. I'm probably also going to import random, because we said we were going to randomly place those things on the screen, so let's import that for right now. And now let's go ahead and create that block, or that class. So the first class that we had looked at was that block object. So there's the block object class. And what we're going to do is let's make the constructor first. And we're going to pass in the X and Y of where we want the block to be, the surface that we want to make the block from, whether it collides or not. I'll set the default for that to true. And we'll set the collide type equal to none as the default. Okay, so there's the start of this. Now we're going to just fill in the code here that goes with that. So the first thing we're going to do, self.x equal x. So we're taking in the parameters that are passed in, and we're going ahead and making those object variables or instance variables here. So okay, and really that's all that I'm going to store in there for right now, is basically just x, y, surface, and whether it collides or not, and whether, if it does collide, what is the collide type. And the other things we need for this block object, really, that's all we need. For example, even the width and the height, notice those aren't in here. We probably ought to add those to this object. But what we're going to do is we're going to get those from the surface that was brought into here. So rather than having those passed in, we're just going to use whatever the size of the graphic of the surface was that was passed in here. So I'm going to do self.height. And to do that, we're going to read it right off the surface. So surface.getHeight. And this is a Pygame surface, so it has a getHeight method. So we're just going to say, hey, whatever that graphic is, let's get the height of it and call that the height of this block. And let's do the same thing for the width. Oops. Get width, and then this is going to be width. All right, so that's all we need for the block object. And then we said the other, or the block object class, the other type of class we said we wanted this world class. So let's go ahead and make that. So class, the world object. Now, the world has a width. It has a height. Those are required things to pass into that. And then we also said it had a screen window kind of position. So in other words, we want to know where is the window into that world. So, and we were using the world coordinates versus screen coordinates, so I'm going to call it screen. And we call that screen left in that source code. We're going to start it at 0. And the screen top. Let's start that at 0. And then the screen width. Let's go ahead and make that 800. We'll do 800 by 600 for right now. But notice since these are parameters that we're passing in, we could change this to something else we want. So screen height. Let's set that equal to 600. Okay, so there's my initial line for the constructor there. Let me make this just a little wider here. I can go a little wider without cutting it off. There we go. Now, inside of this, all we're going to do is we're going to set all of those things. So self.height or width, self.height, self.screen left, screen top, okay, so there, I probably shouldn't hard code these here. All right, so that has set up all of those, and the only other thing we said we really needed to add to this world was ultimately it needs to keep track of a list of blocks. So here we're going to go ahead and add our block list. And we're going to start out as empty, no blocks in the list. Now the first thing I'm going to add here, the first method I'm going to add to this is the ability to essentially add a block to this. So here, def add block. And let me be consistent here in my naming of these things. Where I have all these words here, I'm going to camel case these. So screen left, screen top, screen width, screen height, and then block list. And let me do the same thing up here on these. Left, top, width, height. All right, that makes me feel a little bit better. All right, so now add block, the add block method. Essentially, what we need to pass into that to add a block is we need to know where it is in the world. So in other words, where is the left and top of it? So we could say block X, but I'm going to go ahead and use left and top since we used up here. So block left. We need to know where the top of it is going to be, block top. And then we also need to know what surface it has. So what surface is it? So block surface. And I also need to know whether it collides or not, and I probably want to know a collide type for it if it does collide. So here, we'll say block collides, and I'm going to go and make that true by default. We'll make that none by default. All right, so now to write the code for that is really easy. We just need to create one of these block objects and add it to this block list. So to create the object, we're just going to call the constructor, and then what we're going to do is append that to the list. So I'm going to do self.blockList.append. Now, what are we going to append to the list? We're going to append a block object. So we're going to create an instance of one block object. And if you remember the way that you create the block object, we can actually see it right on the screen there. We're going to pass in this X and this Y, which is kind of the left and the top. So this is going to be block left, block top. So that's my X and my Y. And now we need to pass in, the next thing is the surface. So the surface here is just going to be block surface. The next thing is whether it collides or not. So here, block collides, and block collide type. Okay, and so now we have an add block method that we've created. And now, before we go on any further, let's go ahead and add the method to render these things. So def render blocks. In render, we don't really need to pass anything into this. It's just going to render all of the blocks based on wherever the screen currently is. So it's going to use the screen Windows definition and the list of blocks to draw them all on the screen. Now, to actually perform this render, what we want to do is just render all the blocks. So we're just going to make a for loop. So for block in self.blockList. So we just go through the entire list, one block at a time. And then what we're going to do with that block list is we're just basically going to do a blit to the display surface. So display surface, notice I haven't defined that right now. That's going to be a global variable that it gives us access to the display surface from Pygame that we're going to fill in just a little bit. So dispsurf.blit, we're going to blit to that display surface. And what we're going to blit, the way blit works, as a reminder, is we need to pass in the first parameter is the surface that we want. So we want the surface of the block that we're on. So we're going to say block.surface. And then the next thing here is going to be a pair that is the X and Y position we want to blit to. Now, you might think that we'll just do block.x and block.y. But there's a little bit of a problem there that we're blitting to the screen, and the block X and block Y are their position in the world. So we need to convert those into screen coordinates. So we're going to do block X, and we do block X here. The way we convert to screen coordinates here is block X minus self.screen left. So again, same way we talked about with the the tile-based system. We're just converting from world coordinates to screen coordinates. And over here, block.y minus screen top. So now you'll notice that we have all of those being blitted, every block one at a time. Now there is one thing that I probably ought to do here, and that is one of the important things to note here is that depending on how we place the camera, the screen, these could be floating point numbers. And if those are floating point numbers, then subtracting that floating point, that number with a fraction from this other number, could result in a fraction. And blit wants these to be integers. So the last thing I'm going to do here is just wrap these with an int around that one. And wrap that with an int. And normally Python will go ahead and automatically perform that conversion for us, so it won't be a big deal. But with Python 3.8, they started giving warnings that it's deprecated to assume that it can automatically convert for you. So we'll just be safe and go ahead and convert it to integers ourselves. All right, the last thing that I want to do here inside of this is, just like I did in that example code that I posted, let me move this down a little bit so you can see a little easier, is I'm going to go ahead and make a giant rectangle around the entire screen. And to do that, we'll just do a pygame.draw.rectangle. And that pygame.draw.rect, what that takes is essentially in this case, the display surface that we want, or the surface we want to draw it to, which in our case is just dispsurf. The next thing that the rectangle takes as its parameter is the color. So I'm going to give it kind of a brightish, reddish, pink color to that, so it's easy to see. And then the next parameter it takes is the rectangle itself for the position. So this would normally be like the upper left corner, which would be 0, 0, and then the width is going to be self, since this is the world, self.width, self.height. But there's a problem with doing it at 0, 0 is this pygame.draw.rect takes things in screen coordinates, not world coordinates, but 0, 0 is in the world. So we need to do a conversion on that. So we're going to do 0 minus self.screen left. And again, same thing as above. We don't want to draw a rectangle on a non-integer location, so I'm going to wrap that with an int. And then I'm going to do the same thing over here, 0 minus screen top. And I'm going to wrap that with an int. Okay, so now we have our giant rectangle around the whole thing. And let's see, that should finish up there. But we've got one more parameter to worry about here, and that is how many pixels wide is the rectangle, so we can see it pretty easily. I can put 3 on there, and then I'll close off that rectangle. Now we have our entire rectangle across the entire thing. Now, we're going to add the collision code in here for our next. So this is collide blocks. And collide blocks, just how we had it before, notice with this, we need to know what we're checking for collision against. So we can't just have self like we would for render. We need to pass in this. So what I call this on the example code that was on the presentation was something like collide left, collide top, collide width, collide height. So that's the rectangle that I want to check collision against. And the way that we're going to check this collision, we'll do it just like I did in the example code. So we'll make this collide type list. Started out as being empty. We're going to make our collide rectangle equal to a Pygame rectangle or Pygame rectangle object. Okay, so Pygame dot, and to make a Pygame just a generic rectangle, there's a class for that, Pygame.rect. And then the way that the Pygame.rect works is we just pass in the left, the top, the width, and the height. So here, let's go and pass in int collide left, int collide top, int collide width, int collide height. And there's my rectangle that I'm going to check collision against. And now to check that collision, what are we checking it against? We're going to check it against every one of the blocks in our list. So again, for block in self.blockList, just like we did before, for rendering them. But this time, as we go through them, we want to see if they collide. So what I'm going to do, but I only care about them colliding if that object has its collides set to true. So if it doesn't have it set where it collides, we're going to just skip it. We're going to ignore it. So we're only going to do that. We could also have said here, if block.collides equal false, then continue. We're going to do it this way. So if it is set to collide, then the logic that we're going to do there is now check collision. So to check collision, I'm going to say if rectangle dot collide rect, which is built into every Pygame rectangle object has the ability to do that. And the way collide rect works is relatively simple. That's on the rectangle of the object we want to check. We just need to pass in the rectangle of the block into this. So here, block dot x, block dot y, block dot width, block dot height. So we're going to say that, and if that comes up to be true, that means that it's colliding with that block. So that's where we need to add it to the list. So here, collide type list dot append block dot collide type. Now, this could add multiple blocks to that that are colliding at the same time. So what we might want to add in here is wrap this as in an if statement that says if it's not in the list, add it. So here, if block dot collide type is not in collide type list. So if it's not in our collide list, then we add it to the list. All right, so now we're at a point where once we get through this for loop, what we will have is a collide type list that is either empty, meaning we're not colliding with any of the blocks in our list, or it is going to have some stuff in it. So what we want to do is say if the length of that list, so if the length of the collide type list is 0, we're going to turn false. We could, like I said earlier, we could return none. Otherwise, and there's no reason for else there because we will have already left, so return collide type list. Okay, so now we have our world object pretty well put together. And so what I want to do before we actually test this and do some stuff with it is I'm going to go and add a player class as well. So the player class, we want to have somebody be able to move around in the world and do stuff in it. So I'm going to do, let's just call it player. And this is going to be a relatively simple class here. But we want the player to start out at some x and y in our world. And we're going to go ahead and pass in a surface that we want the player to be created with. And we'll use that eyeball thing that we had before so you can see the little guy running around in the world. Keep it relatively simple. But let's do self, x, y, and a surface. In other words, it just says here's where it is on the screen. This is the top, or the left and the top, and there's the picture that we're going to see. Now, the thing I'm going to have inside of this, self.x equal x, self.y equal y. And I'm going to go ahead and do a self.surface. And because of the way that I want to handle, so that just puts those three things in, but because of the way I want to handle motion of this, I'm going to give it a differential in x that's going to keep track of the velocity. So self.dy equals 0. So in other words, these are going to be the velocity components as this thing moves. So this is the differential in x. How far is it changing in x? How far is it changing in y each time? And notice that I'm starting at a 0, so it's stationary when this starts out. It's not moving at all. So this is kind of like the velocity vector. We could call it vx and vy. I like dx and dy because it's a difference in x and a difference in y are kind of the two components of the velocity change. And we're going to end up using those later on. I'm also, just for convenience and for symmetry, I'm going to go and put the width and the height. So self.width, so this is the width of the character. So let's do self.width equal surface.getWidth and self.height surface.getHeight. Okay, so now we've got the all of the stuff we need for the player done there. Let's also make a way to render this. So let's do def render. And since it already knows its x and y position, we're just going to use those. So the x and the y position here, we're just going to use the built-in x and y that we already have here. So in other words, we don't have to pass anything to render. It already has the surface in here. It already has the x and the y. so we don't really need any of that. All right, so for render, all we're going to do is on our display surface, we're going to do a blit, just like we did with everything else. The surface we're going to blit from, self.surface, and then the location we're going to blit to is going to be int of self.x minus. Now, here's where we need access to the world, but just like the display surface was a global variable, I'm going to use the world that we create as a global here as well. So I'm going to say world.screen left and int self.y minus world.screen top. Another alternative to this would have been to pass in the reference to the world and store it inside of the player object. But we'll just use it as a global for this example. All right, so now we have a render. And then ultimately, we're going to want to add some code to be able to move this player around. So what I'm going to do is I'm going to go and add a move left. That says more left. Move left. And to move left, what we're going to do is we're not going to change the x or y right now. We're just going to set the dx to that. So in other words, the dx just needs to change here. So I'm just going to say self.dx. And let's do, to move to the left, that's a minus equal 1. So in other words, we're just going to change, we're going to add a little bit of velocity in the negative direction when we try to move left. I'm going to do the same thing for move right, except it's going to be plus equal 1. All right, so we've got move left, we've got move right. And just to make this a little more fun, let's add the ability to kind of add a hover capability. So when you press, let me make it so it's, later on we'll make it so it's bound to the E key, but I'm going to call it move hover. And let's say when you press the hover key, it's going to set the dy. I'm just going to hard code it to be equal to 4. So in other words, it's going to, we're essentially setting the change in y to 4 pixels, so it's going to move kind of just gentle upward direction. Notice we're not adding acceleration to this. We're just hard coding it to be in that upward direction. Also notice that that's decoupled from the x movement to dx here. So you could be hovering while also changing the dx. But this is no matter what dy is, it's going to set it exactly at 4, which is going to kind of move it kind of in that upward direction. And actually, we probably ought to make this -4 since 0 is at the top. We want it to not go down the screen when you press hover. You want it to move up the screen. So it's going to become more closer to 0 as we go up the screen. So we'll put that as -4. And one other one that we're going to fill in a little bit later is we're going to add the ability to have this thing jump. And I suppose we could go and add that now. Yeah, let's go and add the jump now. So let's say move jump. Now, to move and make this jump, there are a couple things we want. In other words, what we're going to do is we're going to say self.dy, and I'm going to say equal -20. So that's going to like apply a large force in the upward direction, moving the thing up the screen. But it's going to just apply that. But in order to apply it, we don't want to always apply that. We only want to apply that if we're standing on a platform. And so to do that, we might also want to add that so if we're standing on the bottom of the world. So in other words, if we get all the way to the bottom boundary of the world, we don't want to fall through it. So we're going to contain people in there. So what I'm going to do here is when they get to the bottom of the world, I'm going to allow them to jump too. So I'm going to say if self dot, let's say this is the player, so self dot y plus self dot height. So if self dot y plus self dot height ever gets to be greater than or equal to the world dot height, that's that global world object again, that's one of the cases where we want to jump. And I'm going to say there's another case, so I'm going to use an or if world dot collide blocks. I believe that's what I called it. Let me go up and check real quick. Yep, so world collide blocks. And the thing that I want to check for collision with is going to be basically self.x, self.y, self.width, self.height. So this is the little rectangle of just the player that we're checking against the collide blocks. And if that comes up, and let me set it this way, if that comes up with something in it, something collidable, I could add collide types to the bricks or the platforms and say platform or something like that and allow that to happen. What I'm going to do here instead is I'm just going to say if that is not equal to false, that means we're touching something that's collidable. And in that case, allow them to jump. Okay, and so that's mostly it for the player. There's one other thing we have to do. We haven't actually moved the player anywhere yet. We just set the dx and the dy based on whether they moved left or right, or hovered, or jumped. We need to actually update the position of that. So I'm going to create an update for the player here. And all that's going to do is apply the change in dx, apply the change in dy, and then do something with that. So to do that, let's do x plus equal self.dx. So I'm just applying self.dx to self.x, and then do the same thing y, self.y plus equal self.dy. Now, you might think that's good enough, but there are a couple other things that we need to consider here. Hold on, I gotta move the cat, it's attacking my hand. Say bye. But there are a couple other things we need to consider here. One of them is that when I'm moving, if I let off of a key, I probably want to have it like slow down slightly. In other words, adding something like friction that kind of slows it down a little bit. So in order to do that, I'm going to do self.dx times equals 0.9. So in other words, that dx loses some of its kind of value. This will shrink down towards 0. It'll lose some of that kind of over time. So if, in other words, if I stop pressing keys, it'll go down to, and let's say I'm running at 10, it'll go down to 9, and then it'll go down to 8.1, and it'll slowly get smaller and smaller and go towards 0. So in other words, when I let off keys, it'll kind of slow down and glide to its stop. It won't instantly stop because, so this is modeling something like momentum, that we have momentum, and then it slowly is going to lose some power due to friction with the air. We could add more friction if you're standing on a platform and less friction if you're going through the air. I'm just going to model it very simply like that. Now the other thing though is that when I'm moving along the x, where I moved this x position here, there's something that can happen where what if I run into a block when I'm moving? What if the new x position that I went to collides with a block? So we probably ought to check that too. So what I'm going to do is I'm going to say if, and I'm going to look at the world again. We actually already have this code up here, world.collide blocks. And actually, because it's the same as the test we just did, I'm just going to copy it from up here. Let me just paste this in down here. So in other words, if the new position that I just went to collides with that block, in other words, if it's not false, it's colliding with something, and the new position that I just updated, notice this position changed because I changed x. So if a change in x caused it to collide with a block, then that means that I ran into something. So I need to self.dx times equal -1. So that's going to invert the dx. So in other words, we're kind of switching the direction the dx is going. And one of the things we might do is we might want to make it so we lose some energy there too. So let's do 0.6. So in other words, we'll not only invert it, but we're also going to be 60% of the energy we had when we hit the thing. So if we hit at a speed of 10, we'll bounce off, but now we'll have 6. So we've lost some energy in that collision. And we can make these variables and adjust them. You can make it so, depending on the type of thing you bounce off the trampoline wall, it inverts your direction, but it adds energy to it. So you go faster off of it than you bounced into it. So that's the kind of thing that we could play with if we wanted to. But right now we're just saying if I collide with that, do that. Now there's one other step here that I need to do that. And that is I inverted my dx and reduced it, but I probably want to move back to the point where I wasn't colliding with the wall. So to do that, I'm going to add a little while loop here that basically says while, and this is going to be, there's probably a better way to do this, but what I'm going to do is while I'm colliding with this, then I'm going to move back the way I came from. So in other words, if my self.dx is greater than 0, so if it's greater than 0, then self.x, that means I came in the kind of, I went over in dx. So here I'm going to do minus equal 1. So I'm going to move 1 pixel back if my dx is positive. If my dx is negative, then I need to add to move ahead. So the idea of this is moving it back to the point where it was no longer colliding. So that while loop will handle, I'm going to move it 1 pixel, check, move it 1 pixel, check, move it 1 pixel, check. And there is probably a much more efficient way to do this. For example, we could have saved off the old position of x, and then if we ran into something, move back to the old one. But then that might be a little unrealistic too. So this is going to move us right to the point of collision. And then the self.dx here, we're inverting that. So now we're going in the opposite direction, but with some energy loss. All right, so that's my movement for x. There are probably a couple other things that we want to do here as well. And that is, what if I want to handle bouncing off of the edges of the world? So if self.x ever gets to be less than 0, then self.x equals 0. And again, we probably want to invert the dx just like we did here. So that's the left side. We also have the right side of the word, so self.x. And I probably want to handle the width of the thing plus self.width. If that ever gets to be greater than world.width. So if that ever gets to be greater than the width of the world, then we want to say self.x equal world.width minus self.width. And then we're going to do the same thing and invert dx and change the energy, or lose a little bit of energy. All right, so there we have x. Now we're going to do something similar to dy. Now, one of the things about dy, though, that we're going to do is before we actually apply dy, I'm going to add a little bit of kind of a fake implementation of gravity here. So to do that, that's just a constant acceleration in the downward direction. So I'm going to say self.dy plus equal. And just to keep this simple, I'll say 1. So in other words, this is 1 pixel per frame that we're adding to dy. But one of the things that I probably want to do with that is I want to put a cap on that. So in other words, if dy ever gets to be greater than, we'll just put a cap on it, 30. So this is kind of like terminal velocity. If we ever get to be greater than 30, then self.dy equal 30. And the 30 is kind of arbitrary. If we want things to be able to move faster or slower as the maximum speed along dy, then I'm going to go and do that. Now, I'm also going to go and add that in the negative direction, a bound in the negative direction too, and say if it's ever less than negative 30, then set it equal to negative 30. So this is just bounding, giving it a terminal velocity along dy. Now we're going ahead and applying that. And now we're going to do the same logic we did up here if it collides with something. So if this collides with something, then we're going to go ahead and do some stuff with that. So here, I'm just going to copy that block, paste it in right there, and then we're going to change some things around. So if the block is colliding when we moved it along y, then we're going to do this same logic we had here, but this is going to be if dy, then y, y, and down here, invert in y, so change the direction when it bounces. And then down here, if y is over less than 0, then set it equal to that, dy, y plus, instead of width, this needs to be height. And this needs to be world.height. Height for these two. This needs to be y, and that needs to be dy. All right, so now we have our player object that's created. So let's go ahead and move on to actually creating a world now, and then putting some of those blocks into it. So we've got all of that other stuff created. So let's go ahead and now the main program. So pygame.init. We're going to use Pygame. We need to initialize it. We also need to make that display surface, which we've been calling dispsurf, equal pygame.display.setMode. So this is actually how we're creating the window. We'll make the window 800 by 600 to match our window size that we specified earlier. And then, so that's creating that. Now the world object, we've been calling that world. That's the global. But to create an instance of that, we're going to call the world object. And the world object's constructor, we're going to make these 10,000 by 10,000. And now we're ready to load up some of our textures. So let's do brick. Pygame.image.load. And the thing that we're going to load in here is going to be brick1.jpg. So that's just loading up the surface. So this is just loading a surface, not really doing anything with it yet. We're just loading it. And let's load some of the other ones. Let's see, we had a beam. That was actually in a file called beam.gif. And we also had a metal beam, which is in a file called metalbeam.gif. And then we've got a that pillar. So let's do pillar equal. And that is a pillar.gif. All right, so that has loaded the, let me add a couple comments here. So that's loading the textures for the blocks. Okay, now, as in our example code, we said we're just going to randomly throw things into the world. So we're not going to really put any thought into this or design, just to quickly test this. So the way we did that, I did that earlier. So here I'm just going to say randomly create some world blocks. So what I'm going to do is just use some for loops and say for I in range. And I believe in the example we did 30. And we did 30 of world.addBlock. And as a reminder how addBlock works, let's scroll up and take a look at that. So this is no world object. addBlock, we pass in the left, the top, or the X and the Y, and then the surface, and then whether it collides or not. So in our case, what we're going to do, the left here, I'm going to make that a random number. So here I'll just say random.randint, and I give it a range here. So I'm going to allow it to be kind of anywhere in the world. So from 0 to world.width. And for the second thing, I'm going to do the same thing, except it's going to be 0 and world.height. So there's my x and the y for the block. And then the surface here, this is going to, I'm going to go ahead and make these pillars. So it's going to be pillar. So just put the pillar texture there. And I also going to, let's make the pillars kind of a background object so they aren't going to collide. So the collides is going to be false there. So I just created 30 of these pillars randomly throughout the world. And now let's go ahead and use this same logic to create some other things. So here, let's make some bricks. Let's make 200. Actually, let's make more than that. Let's make 300. I'll make it match the slide. So 200 of these blocks. It's going to be the same thing we have here, except these are going to be brick. And this is going to be true for collides. Or since the default was true, I could just leave that off. But for, I guess for clarity, we'll go and leave it on there. All right, so there's 200 of those. And then the last kind of group of things that we want to create to make it match what the slides were. I believe we did 40. And the world blocks we're going to add here. I'm going to add 40 of the beams, and then 40 of the metal beams. So this is going to be the same line. I'll just copy and paste it. So 40 beams, 40 metal beams. So there's all the objects that we're adding to our world. I guess the last thing we need to do is we're going to need to load or create a player object. So player equal player. And let me do one thing here quickly. To make this a little more clear in the code, I'm going to call that player object. So down here, we're going to create an instance player object. And the player object required us to specify some things. Where is it on the screen? I'm just going to start at 100 to 100. Remember, that's in world coordinates. And then I'm also need to specify a surface for that. So here, I'll just put iSurface. And that's going to be pygame.image.load. And the image that I want to load for that I is i2.png. Okay, so now we have our player object that's been created. So now we're ready for our main loop. So while true, so this is my game loop. What I'm going to do here is, the first thing is I want to lock my frame rate. So we've done this before. FPS clock equal pygame.clock or .time.clock. And what pygame.time.clock does is that's going to create this frames per second clock that we're going to use. Let's say for clarity, let me go ahead and camel case this for consistency. And then we're going to do FPS clock.tick. And I'm going to go ahead and run this at, let's do 60 frames a second. Okay, so now inside of this loop, we're going to need to do the stuff we need to do to make the game work. So the first thing I'm going to do is pump the event queue so we can get input events coming into our window. And then I'm going to check the keyboard state. So keys equal pygame.key.get pressed. So that's getting which keys are pressed. And now to make this super simple, I'm going to say if keys pygame.k_escape. So if they press the escape key, we're going to break out of our game loop. Now, what are we going to do on other key presses? Let's add some for movement here. Let's say if they press K_A, then we want the player to move to the left. So here, player dot move left. So remember we created those things there. So player.move left. If they press D, we're going to move right. We also had jump. And hover. Let's do hover with E. Now for space. Space is going to be a jump. So we're binding which key causes what thing to happen in the game. And that was really all of the input that we had for right now. So now that we're at that point, I think we're ready to actually do a couple of things. The first thing that we want to do is maybe let's clear the screen. So that's going to be display surface.fill with black. So that's going to clear the screen. The next thing that we're going to want to do is we're going to want to kind of update the player. So we're going to update the player's position. That's based on the input. And really, let me move that up here before we clear the screen. So that will keep all the rendering together without other logic stuck in there. And now let's go ahead and render the blocks. So world.render all the blocks. Player.render. And then now that we've rendered everything, we'll do an update of the display. And then after the loop, pygame.display.quit. Okay, now that we're pretty close to what we want now with this working game. There's one thing that's missing. Let's go and try this and see what happens. We may have some. Oh, we missed an indentation here. Let's try again. Okay, so what do we have here? Screen left is not defined on line 19. So let's look at that real quick. Okay, so I just missed changing some capitalization here. Let's try again. Now problem line 29. Okay, this needs to be self-dot. Okay, now you'll notice that it worked. There's a beam that was randomly generated, but the eyeball fell off. And you can kind of see this. I don't know if you can see it or not, but this is like a red thing. That's the boundary of our world. So one of the things we don't have right now is we don't have the camera following the player. So to add that, there's a couple ways we could do that. We could add that to the world and say world.lookAt and pass in a position. That'd probably be a good way to do it. Or we could just update the camera position in our main program if we wanted to. So we have a choice of one of two ways of doing that. Let's add it just to our main program first, and then we will fix that, how the camera follows, and move it into the other place later. So what I'm going to do is just in my main code here. So I updated the player's position. So now this is going to be we'll just say update the screen to follow the player. And the way that we're going to do that is going to be, there are a couple ways we could do it. We could hard slave it to the player. We could make kind of soft follow so it tries to keep the camera or the player in the center of the thing. Or there's a method where when you get near an edge, it pushes the player along. So I'm going to do that one. So in other words, I'm going to say if player.x minus world dot screen left. So in other words, we're taking player X and we're converting it to screen coordinates. So if the player X's screen coordinates are ever less than world dot screen width times, let's do 0.4. So what that's doing is saying if I'm ever less than 40% of the width of the screen over toward the left, then that's where I need to now move the camera. So where am I going to move the camera? Say world.screen left. I'm going to set that equal to player.x minus world.screen width times 0.4. So in other words, I'm saying if I'm ever less than that, then move the camera over so that I'm at that position. So in other words, it'll always push the camera over when, so if this is the kind of width of the camera, whenever I get to that kind of 40% mark, as I move over, it's going to kind of push the camera so it always pushes the edge of the frame over with it. So we're going to do that same thing now, but we're going to do it with the other side. So if player X minus screen left, in other words, the world or the screen coordinates of that ever get to be greater than world width times, and let's do point, to make it symmetric, we'll do 0.6. So in other words, we've got this kind of 20% of the middle of the screen where it'll always keep the object. So if we're moving around in there, it won't move. But if we get near the edge in that box, it'll push it over one way or the other way when we get there. So this is the same thing, except at the 60% mark, and we inverted the less than to a greater than. All right, so that handles that. That's moving the player or the camera in the X direction. We probably ought to do the same thing in the Y for it moving up and down. So as it moves up and down, I'm just going to copy these, and we're just going to change the values. They're the variables. So this is going to be Y. This needs to be screen top. This needs to be height. And here for this, let me do 0.25 to allow it to get closer to that. And you can play with this however you want the camera to be set up. And then here, the last one, same thing, Y, top, height. And if that was 25% from the top, this should be 5.75 off the bottom. Okay, so now that's going to push the camera, but only when we get near the edges of it. Let's run that real quick and see if that has made a difference. Okay, now notice that the eyeball can move around in the world, and we'll notice when I get within 40% of the right-hand side of the screen, it moves. If I'm in the middle, it doesn't matter. If I get or 40% of the left or 40% of the right, so 60% of the total screen or 40, it pushes the thing along. Now, notice that one thing, notice jumping is not working, hovering is. So hovering is working fine, but jumping is not. So let's see if we can fix it. Also notice the pillars do not collide. So I can go across the pillars. They're kind of like a background object. So let's figure out why jumping is not working. So that's the only thing that we have that doesn't seem to be working right. But everything else goes through the world. And let's see if I can get to the bottom of the world. Notice this is a large world space here. 10,000 pixels, so I keep running into beams as I go. There's the bottom of the world. Okay, jumping is working on the bottom of the world, so it's just not working on top of other things. So we have a little bit of a problem somewhere in our code. So jumping does work, but just only in certain spots. So we know the collision works, we know that the jump works, so let's actually see if we can figure out why that's not completely working. So we know when we press space, it calls move jump. So it's got to be in the player move jump somewhere. So move jump. We know this part of the if statement works. It's got to be something in this collide blocks. that's not equal false. So that looks right. So it's got to be maybe something in collide blocks. All right, so let's go look at collide blocks. Okay, so let me pause the recording for a second. I'm going to debug this and figure out where the problem is, because it looks like that should be right. And let me put a quick print statement in here. If I get down to here, let me just print out that collide type list and see what we're getting as this runs this. So I am getting none. You can see back there in the background all these none things coming up there when I'm sitting on that thing, but it's still not allowing it to jump. So that list is not returning false. All right, so let me add, so we know that that's returning the right thing. Let me take this guy out. Go to the player object where it's jumping. Let me repeat. This. And let me just do a print on that to see what we're getting when we press jump. Oops. All right, now we're on a beam. All right, I'm getting false from there. So somehow I must be passing in the wrong rectangle. So let me take a look at what rectangle I'm passing in there. Self.x, self.y, self.width, self.height. So that looks right. Okay, I bet the problem here is that when we do this jump, we've been moved back to a point where we're no longer colliding by the update portion of the loop, so we will never be colliding. So I think what I need to do here to make this work is I should look one space below where I am when I do the check for the jump. So in other words, what I'm going to do to fix this is that everything is working as expected. We're just not quite checking the right place for the collision here. So what I want to do is I need to say not where I am is that colliding, but I need to say let's do one more pixel ahead in the Y and check that. So I think that should fix it. And there we go. So the problem was that the update was moving us back so we were no longer colliding, and they were saying, hey, are we colliding? So this is actually moving our rectangle just down one pixel and saying, are we colliding if I'm one pixel below that? And I am. So in other words, I'm saying, is there something below me that I collide with? If there is, then I'm allowed to jump. So now notice I can jump and I can move through this large world. And notice there are a lot of things in the world. And a couple things to notice about this. I can jump and bounce back and forth on those things. But notice that, also notice the bouncing. That's us inverting that dy to make it, but losing some elasticity in it every time. Same thing if I jump against the side of something like that. It bounces off. And notice when I let off the keys, it takes a little while for it to come to rest. So press, release, it'll kind of slide to a stop as if it has momentum. All right, so let's do one final thing in this example, and then we'll call it done for now anyway. The final thing I'm going to add to this example is, what about an enemy? Let's add an enemy to this. We have a player object. Let me add a little enemy that chases after the player, kind of like a ghost or a demon or something like that. And to add this enemy, I'm going to keep it super simple to get it done quickly. Let's do class, let's call it a blob. And the blob, we have this constructor. The blob, I'm going to put it just at a position on the screen. So let's just do X and Y. And if we wanted to, we could add a surface, but I'm just going to draw like keep this super quick and just add a circle or something like that. So the blob itself, self.x equal x, self.y equal y. If we wanted to, we could have it be animated and change shape or whatever. I might do something like that when I render it, but I'm just going to give it kind of an x and a y for right now. And I suppose we could give it like a size or something too. All right, so we're going to have a render for the blob. And again, to render this, we're just going to do a circle. So Pygame.draw circle onto the display surface with a color of, let's make it kind of a gray color maybe. Maybe a bluish gray. And let's go ahead now, so that's the color of it. Now we need the center of the circle. It's just going to be self.x, self.y. But again, remember those are in world coordinates. So we need to convert it. So self.x minus world.screen left. And since screen left can be a fraction, we have to convert that to an integer. We should. And then the same thing to convert this. So int self.y minus world.screen top. Now we need the radius, which I'm just going to do self.size. And let's make it solid and filled in. All right, so there's my blob. Now, one thing that I'm going to add to the blob also is kind of a ability to move. And I'm going to make it so the blob kind of hovers over things more like a ghost, so it doesn't really need to check much when it moves. But I'm going to make a move towards thing here. Then I'm going to pass an x and a y into this. So in other words, the blob is going to kind of move towards that place in the world. So that's in a world coordinate. So all I have to do for that is say if self.x is less than the target x, then self.x plus equal 1. That should be self.x. Okay, so in other words, I'm saying if the blob's x is less than the x it's targeting, then we add to try to get there. We'll just do the same thing. We'll say if self.x is greater than x, self.x minus equal 1. Could have put an else there, I guess. And then let's do the same thing for y. So if y is less than y, then add to our y. If our y is greater than their y, then subtract from the y. All right, so now we have this kind of move towards feature that we've implemented. And that's going to allow this to move it. So what I'm going to do down here in my main program now is first I'm going to create a blob. So I'll call it blob equal blob object. And we're going to pass in a, let's do 400, 500 is where it starts. And its size, in this case, let's just make it 50. So there's our blob object. And now in my code, all I have to really do is kind of move the blob towards the player. So let's do that up here. Let's do blob dot move towards. And if you remember move towards, how it works, we're just going to pass in the x and the y that we want to move towards. So in this case, it's just going to be player.x, player.y. And now we need to render the blob. So let's render it all the way to the top here. Blob.render. All right, let's see if that works. All right, there was the blob. It's coming after us. Here, let me hover back up there and see if we can find it. It's moving very slowly towards us, but it is moving. We should come across it here at some point. There it is. And notice it's chasing us. Or it should be chasing us. Let me sit on a block here and see what happens. Okay, so it was chasing us. The only thing it's targeting, though, is it's targeting the upper left corner of the eyeball rather than the middle of the eyeball. But you'll notice it's trying to, it's like can avoid it, but it does chase after us in the world space. The blob is moving through world space, and if we wanted to, we could make it so the rendering of it looks a little more interesting than that. Right now it's just a stupid circle that's following us. We want it to look more blob-like and a little scarier. Maybe we just change the rendering part of that a little bit. And let's do something with that real quick here. All right, so right now we're just doing one circle. Here, let's do 4. Let's do 10 circles, and then let's kind of jumble them around a little bit here. So I'm just adding some offsets in here, and then what I'm going to do is every time for the loop, I'm just going to calculate a new offset. So Pygame, or let's do offset x equal we'll just offset x and offset y equal to those numbers. Let's see if that looks a little more blob-like. Yeah. Yeah, let me hover immediately. Okay, that looks a little scarier. Maybe still not super spooky, but a little better than it was. Now it's a vibrating monster. It doesn't move really fast, so it's not exactly hard to avoid, but imagine if we had a bunch of those going around our world. It'd be suddenly a harder game, and it's just a right height that we can jump over it if we're careful. Okay, so let's go ahead and stop there. Let's go back to the presentation just for 1 second here. All right, so this is where we finished up. We finished up with the code that we had added. And kind of the final thing in this, the summary, is that block worlds have this kind of alternative way to represent large worlds. And notice we made a world that was 10,000 by 10,000. We didn't really have to worry about making a file with all those grid things. We just put the object wherever we want them in the world. In this case, we made it randomly. And so it doesn't have the limitations and restrictions of a tile-based world. We don't have to make that giant tile structure. We just make rectangular block objects, put them wherever we want to. Now, one thing, improvements that I would suggest, you can combine this concept with the tile-based worlds relatively easily. to have some elements that are varying sizes mixed in with the tile-based world. Another thing you could do is we could improve the efficiency of this by only rendering items that collide with our screen rectangle. Right now, you'll notice that, and let me just switch back to that code just for 1 second here. You'll notice in our render for the block world itself, which is right here, notice we're not checking it. We're just saying, hey, for every block, blit it to the screen. We're letting Pygame figure out whether to skip the blit or whether to perform the blit. We could come up with some slick ways of, or just a rectangle check to say, does this block collide with the screen? If it does, then draw it. If not, skip it. So we could add that relatively easily. Now, kind of finishing this up here, that we could add that. We could also have the ability to have the blocks move in the world. So in other words, the blocks don't have to be fixed like tiles do. In other words, we could make beams that, or even the block object have a movement function that gets called, or we can make a class, subclass of those, so that you can make something like, rather than have the beams all be stationary, they kind of slowly go up and down, or something that works like an elevator where it goes up, it stops for a while, and then it goes down. And as long as we're moving that block together at the same time, you can make things that are like blocks that kind of have other things that control the position of them. And since they can be positioned anywhere in the world, you could have something where, for example, you have blocks that kind of are lined up that make water, and the parts of the blocks kind of go up and down relative to the some kind of pattern that's programmed with them. And so that ability to move things around, and not in tile chunks, but in any world coordinates we want, can be really useful. And kind of here's where we finished up. Again, notice the eyeball sitting on this platform, but it can go in front of that. And notice that the blocks can be any size, any shape. We can make little single tiny pixel blocks that things can collide with. We can make really large things that collide with. We could give them each a collide type and say, this is a platform, this is a pillar, this thing is made of fire, so it hurts you when you hit it. This thing is spikes, so it takes damage. This thing is a, when you touch this thing, it's a keep or a pressure point type collision box. So when you touch that, then it opens up a door somewhere and starts a timer. There are all kinds of things you can do with a collision type thing. So you can say, if in the list is a thing that catches on fire and you're holding a torch, then that thing gets burned up or whatever. All right, so that's all for today. So stay safe. I will post everything to the course page, and you might want to, next class we're going to talk about some other physics simulation stuff. I did look through the survey that I put out there, and it seemed a few people didn't like the YouTube video, but when I ranked them and scaled them, it was like a 2-to-1 ratio of people that liked the YouTube presentation versus a Blackboard kind of way of doing it. So we'll do this at least for probably the rest of this week. We might switch it up next week. But until then, stay safe, and I'll post the code, and I'll post the, we might have a quiz that shows up on the course site, so just watch for that.